In this class, we are trying to understand what is a crystal, why are they important as far as solid state physics is concerned, and how do we represent them. You will also be introduced some of the important terminologies in crystal physics like lattice, basis, unit cells, crystal structure, etc. What we have in this universe is the matter, and what we are interested is to study the properties of the matter around us. So the matter in the universe has been conveniently divided into the condensed state and the gaseous state. So we have two divisions for matter. One is the condensed state and the other one is the gaseous state. And this condensed state is again divided into the solid state and liquid state. We have solid state and liquid state. So there is again two divisions for this condensed state of matter. One is the solid state and the other one is the liquid state. Now, as you know, in solids, the relative position between its constituent particles are fixed. So the position of the constituent particles are fixed in the solid state, whereas in the case of liquids and gas, these particles are in constant translational motion. So this here, if you look in this liquid state, these particles are in constant motion. The same is true for the case of gaseous state. So what we have seen is that the matter has generally two classifications, the condensed state and the gaseous state. And the condensed state is again classified into the solid state and the liquid state. And the difference is that in solid state, the position of the constituent particles are fixed, whereas in the case of liquid state, the position is not fixed, they are in constant translational motion. The same is true for the case of gaseous state as well, where the particle positions are not fixed, but they are in constant motion. Now we are more concentrating on this solid state of the matter, which is more important for us, and we will be discussing only the solid state of the matter in the first module of this course. So we have seen that the positions are fixed in solid state, but the problem is that these fixed position particles, it may not be arranged in a well ordered manner. So depending the size of the ordered region, the solids are further classified into amorphous, amorphous, polycrystalline, and single crystalline material. So again, the solid state has three classification. Solids can be classified into amorphous state, polycrystalline, or single crystalline. So this is based on the arrangement of the constituent particles in each of these system, or in the solid state. Okay. So the single crystalline materials are sometimes simply called as the crystalline material. So sometimes you can write it as, or mostly when we say that a material is crystalline, that means it's a single crystalline material. Okay. So what is the difference between these three categories of materials? It's purely the arrangement of the atoms. So most of the properties of a solid depends on its atomic ordering, or in other words, its crystalline nature. So among these three classes, the single crystals are the simplest type of materials which could be easily understood by various theoretical models. So in this paper of engineering physics, we will be discussing the properties of this particular class of materials. So an understanding of single crystalline materials will equip you to get some insight into the properties of the polycrystalline and amorphous materials as well. Okay. So let's see how to categorize, or let's see the properties of these three divisions or these three forms of the solid material. Now let's consider a single crystalline material. Suppose you have some material, some arbitrarily shaped material. Let me draw it like this. Now the constituent particles in crystals are arranged in a regular periodic manner in all three dimensions. So let's say you can see that all these atoms are arranged in a regular manner. There is a perfect ordered arrangement of the constituent particles. So you can thought of these materials as formed by a regular repetition of identical building blocks in all three dimensions. Now what is the case if your material is a polycrystalline one? So let's again consider an arbitrarily shaped material. Now here you can see that in polycrystalline materials also we have an ordered arrangement of the constituent particles of the crystals, but this ordered arrangement is not throughout the entire structure of the solid. See, we have a perfect ordered arrangement within a short or within a small region called the grains. Each of these are grains. So within this grain you can see that there is one particular kind of repetition or arrangement of the articles, and within another grain there is still a periodicity or perfect ordered arrangement, but this ordering is different from the other grains what we have here. So within each grain there is a perfect ordered arrangement, but a material as such is made up of many such grains. So we call this small region where we can find a perfect ordered arrangement, we call it as the grains. So one of the important thing is that we have grain boundaries in the case of polycrystalline materials. All these are grain boundaries where the periodicity of the materials changes, and this will introduce several defects and several property changes can happen in polycrystalline material compared to the single crystalline materials. Now what is the case of an amorphous materials? Now in the case of amorphous materials we still have atoms or constituent particles, ions or molecules from which these materials are made of, but you won't be able to find out a perfect ordered arrangement over a long range. So particles may be arranged in a random fashion, or there can be some ordering to the immediate neighbors of the atoms. But if you look this particle or if you analyze the ordered arrangement of these constituent particles over a long region, then you won't be able to find out any perfect ordered arrangement in the case of amorphous materials. So as I mentioned before, the understanding of single crystalline materials are quite easy because you can model these things based on some theory, or theoretical models can be easily applied for these single crystalline materials. The reason is that we have a perfect ordered arrangement of atoms here. But even though we are going to study the details of the single crystalline materials, that will help us to understand these two categories of materials as well. So what we are going to discuss now onwards is the properties of single crystalline solids. So let's see how to represent or how to study a single crystalline material. Now we have seen that the constituent particles are arranged in a regular periodic manner in all three dimensions in the case of single crystalline solids, or they can be thought of as formed by a regular repetition of identical building blocks in three-dimensional space. So what we have is a regular repetition of identical building blocks in all three dimensions. Now, to address the question how to represent these crystals, the scientist Bravais introduced the concept of space lattice. So he introduced something called space lattice. This is also known as Bravais lattice. Now this Bravais lattice specifies the periodic array in which the repeated units of crystals are arranged. So what we have is we have regular arrangement of these constituent particles like these things, right? Now this Bravais lattice tells you that or it specifies the periodic array in which these repeated units of crystals are arranged. So each of these units in a crystal, it may be single atoms, or it can be a group of atoms, or it can be molecules, or sometimes it can be ions as well. So it can be anything. Whatever be these constituent particles, whether it be atoms or molecules, you can find an ordered arrangement in single crystals, and the Bravais lattice will tells you the periodic nature in which these constituent particles are arranged. So the Bravais lattice summarizes only the geometry of the underlying periodic structure, regardless of what the actual units may be. So we may need a definition. So to define it, so let's define this Bravais lattice. It's an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever of the points the array is viewed. So this can be taken as a formal definition for the Bravais lattice or the space lattice. It's an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever of the points the array is viewed. So such points in the space are called the lattice points. So basically it's an arrangement of the points, and you can say that see, we have seen that discrete points, an array of discrete points. So each of these points, they are called the lattice points. They are called the lattice points, and all such points forms a space lattice. Or if you say, if you consider the entire lattice points in the material that you consider, then it forms a space lattice. These lattice points ultimately forms a space lattice. So what is a space lattice, or it is also known as crystal lattice? So a space lattice or crystal lattice is the totality of all such kinds of lattice points, and individual points are called the lattice points, and when you collectively call, we call it as the space lattice or the crystal lattice. And now let's consider a two-dimensional array of points like what I have shown here. So if you consider one particular lattice point, let's say this one, suppose you consider this particular lattice point. So the distance along the x direction to the nearest lattice point is this one. So these are specified by a lattice vector called A, and the distance to the nearest lattice point in the y direction is specified by the lattice vector called B. So to represent the distances of nearest neighbors in a two-dimensional crystal, we need two vectors, and these vectors are called the lattice vectors. And for the two-dimensional crystals, we have A and B as the lattice vectors. Now, to represent the position of any of these lattice points with respect to some arbitrary origin, we can use these lattice vectors A and B. For example, I have shown or I have drawn two axes, one along the x-axis and the other one along the y direction, and I have chosen an arbitrary origin somewhere here. So there is no speciality about this point. You can choose this point arbitrarily at any point on this crystal lattice. Now we want to say that suppose you want to know the position of one particular lattice point, let's say this one, this circled one lattice point with respect to this origin. Now this position can be represented by the vector like this from the origin, and it can be represented by this expression. It's given by n1a plus n2b, where this n1 and n2, it can have any possible integer values. It can be positive, negative or 0. For example, in this particular case, you can see that you can reach this particular point if you move 2 points along the x direction. That is, you have 1 point, 2 point along the x direction, and then 2 units or 2 points along the y direction. So you can see that this is basically, this point is 2a plus 2b. So both n1 and n2 are 2 in this particular case. So in this fashion you can represent position of any of the lattice points using these lattice vectors, or in terms of these lattice vectors A and B. Here you can see that the lattice appears identical when viewed from any position given by these equations. So as I mentioned before, there is nothing special about this chosen point or about the origin. From whatever point you observe these lattice, you can see the identical arrangement of the atoms. So in other words, we can say that the lattice has a translational symmetry. The lattice has a translational symmetry. So we will be studying the details of the symmetry in the coming classes, but just to see that there is some kind of symmetry. That means even if you translate this origin to some other point, let's say to this point, with respect to this point also you can represent the position of any other particles, maybe the same position, same lattice point, using this kind of an expression. So there is a translational symmetry in the ordered arrangement of the atoms. Now this idea can be generalized to three-dimensional lattice, where the position vector of any lattice point can be specified by an expression of the form like this. So if you have a three-dimensional, if you imagine a three-dimensional arrangement of the lattice points like this, then you will be having one more set of lattice points which is positioned along the vertical direction or along the perpendicular direction. So you have three indices. The position vector can be represented by n1a plus n2b plus n3c, where this n1, n2 and n3 are some numbers like what we have seen here, and a, b and c are the lattice vectors along x, y and z directions respectively. So what are these lattice vectors? That will tells you the distance to the nearest neighbor from the chosen point, from the chosen lattice point along x, y and z directions. Okay. So this c is the distance between the lattice points along the z direction. Now keep in mind that these lattice points are actually imaginary structures. Those are not real points in this space. Those are entirely imaginary structures. So how do we get a crystal structure from such imaginary lattice points? So that is what we are going to address. Let's again consider a lattice like what I have shown here. It's a two-dimensional arrangement of imaginary points in space. Now a crystal structure is formed only when a group of atoms or molecules is attached identically to each of these lattice points. So these points will simply tell you where you can expect the positions of the constituent particles in the solid, and these point itself are not the constituent particles of the solid structure. It will give you the positions where the constituent particles of the crystals are going to be found. So those constituent particles can be atoms, it can be a single atom, or it can be a group of atoms, or it can be molecules or ions, whatever it may be. So this group of atoms or molecules is called the basis. So for this particular example, I have chosen the basis as the collection of two atoms. One is a bigger one, this cross shaped, and another one is a star shaped small one. So let me say that this is the basis of my particular crystal structure. Now I told you that these white dots, these are the lattice points, and these are the locations where we have to put these bases, these repeating units. Now when we put these basis structures in the lattice points, the resulting structure is the crystal structure. So this is the crystal structure. Now you can see that there is an arrangement of these elementary units or these bases along the three dimensions, and in the crystal structure each of these dotted circles, like this one, you can see some dotted circles, and these dotted circles are actually the positions of the lattice points. And as I mentioned before, these are simply some imaginary points. You won't be able to, or there is no such real structures or points in the crystal. The crystal in reality, it consists of only a repetitive arrangement of two units in this particular example, and these units is the basis. So you can see that this one is a basis, this one is a basis, this one is a basis, without considering that dotted circle inside it. And when you extend these bases, you will get the crystal structure. So what we have is a lattice plus basis is equal to a crystal structure. Now to describe a crystal structure, it is often convenient to subdivide the structure into small repeat entities called the unit cells. So let's see what are those unit cells. So these unit cells can be considered as the building blocks of the crystal. For example, in the two-dimensional lattice shown here, we can choose a parallelogram formed by lattice vectors A and B as the unit cell. So we have this lattice vector A and B, and if you construct a parallelogram from this A and B, this can be considered as a unit cell. Why is it a unit cell? Because we can create the entire structure simply by repeating this unit cell to X and Y direction. So if I repeat this unit structure into X and Y direction, I can construct the entire solid structure that we are going to consider. So that is the concept of unit cells. Those are the building blocks of the crystal structures. Like we have bricks for building the physical structures or buildings, so we have unit cells as the building blocks of the crystal structures, and when we repeat these unit cells along the X and Y direction, you will get the crystal structure in 2 dimensions, and in 3 dimensions you have to repeat these unit cells X, Y and Z directions. Now we can generate the same structure by choosing another unit cell formed by unit vectors A prime and B prime. So here I have drawn 2 other lattice vectors. Let's say this A prime This is A prime and this is B prime, and this is different from A and B because in A and B what we had is we had chosen a unit vector or a unit cell like this, like a parallelogram. But this time we are not going to consider that particular unit cell. Instead, we are going to consider another type of unit cells formed by some other lattice vectors A prime and B prime like this. Okay, so you can see that this is a unit cell because you can create the entire structure by repeating this unit cell into x and y direction for this two-dimensional lattice. So you can see that the choice of a unit cell is not unique, right? There are different ways based on the symmetry of the structure that we are actually analyzing. You can consider or you can construct a unit cell by different ways. So the choice of a unit cell is not unique. Okay, and one more thing is that there are two types of unit cells. It can be a primitive unit cell or it can be a non-primitive unit cell. So let's see what is a primitive unit cell and what is a non-primitive unit cell. A primitive cell is a minimum volume unit cell and it contains only one lattice point. For example, this particular unit cell formed by the lattice vectors A and B, it's a primitive unit cell. Why is it a primitive unit cell? Because you can see that in this particular arrangement of the atoms or the arrangement of the unit cells, let's consider any particular lattice point. Let me say this particular lattice point. You can see that in two-dimensional arrangement, this lattice point is shared by 4 unit cells: 1, 2, 3 and 4, right? So it's a corner position and it's shared by 4 unit cells. So the contribution of this particular unit cell in this particular lattice point into a particular unit cell is only 1 by 4, and another 1 by 4 is contributed to this one, another 1 by 4 is contributed to this one, and another 1 by 4 is contributed to this one, and adding all these 1 by 4 you will get one lattice point, right? So in that fashion you can see that if you add the contributions of these 4 lattice points for this particular unit cell, you can see that there is a contribution of 1 by 4 from this lattice point and 1 by 4 from this lattice point, 1 by 4 from this, 1 by 4 from this. So if you add all these 1 by 4 you will get 1. So this particular unit cell has an equivalent lattice point of 1. Okay, so this, hence we can call this as a primitive unit cell, and it's a minimum volume unit cell and it contains only one lattice point. Now in the case of non-primitive unit cells, like what I have shown here by these rectangular structures with the lattice vectors A prime and B prime, this is also a unit cell. We have seen in the previous slide that you can construct the entire structure by repeating these unit cells along x and y directions. Okay, so this is called a non-primitive unit cells because it's not a minimum volume unit cell and it contains more than one lattice point. How? Because there is a 1 by 4 contribution from here, 1 by 4 from here, 1 by 4 from here, 1 by 4 from here. So we have these 4 corner lattice points those are equivalent to one lattice point, and there is an additional lattice point inside this unit cell. So this is equivalent to 2 lattice points. So such kind of unit cells are called the non-primitive unit cells. Okay, so there are two types: primitive unit cells and non-primitive unit cells. And primitive unit cells are minimum volume unit cells that contains only one lattice point, and non-primitive unit cells there can be additional lattice points, and it can be either on the face of the unit cell or within the unit cell itself. Now the unit cell defined by A and B has minimum volume and it is equivalent to one unit cell. We have seen that. Hence, this is a primitive unit cell, and this one has a larger area, or in 3 dimension this will be having a larger volume. So this is called a non-primitive unit cells. Now in 3 dimensions, the unit cell for most of the crystals are parallelopiped or cubes having 3 sets of parallel faces. In most cases, it will be having 3 sets of parallel faces. Now a unit cell in 3 dimension can be completely described by 3 lattice vectors A, B and C, where A will tell you the distance to the nearest neighbor atom or nearest neighbor lattice point along the x direction, while B and C gives the distance to the nearest neighbor lattice points along y and z directions. Now apart from these 3 lattice vectors, we need 3 angles to completely specify the structure in 3 dimensions, and those angles are alpha, beta and gamma. And you can see that alpha is the angle which is in the opposite side of this lattice vector A, right? And beta is the angle which is the angle formed by these lattice vectors C and A, or it is in the opposite side of this B, and gamma is the angle which is in the opposite side of this lattice vector C. So if you know these 6 parameters, these 3 lattice vectors A, B and C, and 3 angles alpha, beta and gamma, you can specify the crystal structure in 3 dimensions, and these are called the lattice parameters. These lattice vectors and the angles between them, they together are called the lattice parameters. So once you know the lattice parameter, it is very easy to understand the structure of the crystal.